Hey, I'm Dylan. I'm a PhD student at UC Irvine. I'm going to be talking about my work, Feature Attributions and Counterfactual Explanations Can Be Manipulated. And this work is done in collaboration with Sophie Hilgard, Samir Singh, and Hima Lakhraju. So we're going to address the question of how adversaries can manipulate explanations into concealing potentially undesirable aspects of models. So why is this an issue? Why is it bad if adversaries can conceal bad aspects of models? So machine learning models are used in a number of high-stakes decision-making settings today. And in these settings, explanations are used to establish trust. If we want to be sure that models make decisions for the right reasons, we can use explanations to verify that these models do so. And as a result, explainability is really a key part in many ML pipelines. So if we're going to use explainability to establish trust in models, we need to be sure that we can trust explanations themselves. And this is, in some sense, an open question. And what we're going to show is that adversaries can fool people into trusting untrustworthy models by manipulating explanations. So it's possible to design models that do bad stuff, but explanations will not reveal this bad behavior. And as a result, it is not possible to always use explanations to establish trust. So the exact problem setting we consider is similar to classic adversarial attacks, but slightly different. So in this classic adversarial attack paradigm, you have a good actor who owns a model, but a bad actor will send deceptive inputs to get a desired outcome from the model. In our setting, we're going to say that the bad actor is the model owner. So the bad actor wants to put a harmful model into production in the world. At the same time, some good actor, some auditing agency is going to feed inputs into this model and construct explanations in order to figure out if the bad actor is doing bad stuff. So the bad actor is incentivized to fool these audits while executing whatever bad behavior that they desire to do. So they do not want explanations to reveal their behavior, to be clear. In this work, we combine two larger works where we demonstrate that feature attributions and counterfactual explanations can be manipulated. So I'm going to step through how this is possible for both feature attributions and counterfactual explanations. So first, we're going to look at how this is possible for feature attributions. So specifically in this setting, we're going to say that an adversary wants to deploy a bias classifier. And we're going to understand bias as prediction bias. So does the model rely on protected features, such as race or gender, to make predictions? And regulators are going to try and figure out if this is going on using feature attributions, such as Lime or Shap. So you're going to look at individual predictions and say, is race or gender a big factor in this prediction to figure out if bias is going on? So the adversary is incentivized to build a model that has unbiased explanations. So the feature attributions do not say that race or gender is important, yet the predictions still remain biased. So why is this possible for a method like Lime or Shap? And the key insight here is that both Lime and Shap are perturbation-based techniques, and they have heuristic strategies for sampling perturbations. We can see this quantitatively or qualitatively. Looking at the perturbation data and just the original data from the COMPAS data set in a two-dimensional PCA setting. So if you look at this orange data, this is the COMPAS perturbations, or the line perturbations for COMPAS, and this blue data is the original COMPAS data points. We can see that these are quite different. So the strategy that an adversary can employ is they can construct a model that does one thing on this perturbation data and does another thing on the in-distribution blue data. And if they set up their model that it acts biased on the original sort of COMPAS data points, but unbiased on the outer distribution data, Lime will only explain the model behavior on this unbiased outer distribution data. So the model will still be biased, but the explanations will not reveal this bias. And we can see that this is quite effective in practice. We evaluate the success of this approach using this percent occurrence figure. And what this says is for this feature importance explanation, what is the percent of the time that race or some other features are listed as either the first, second, or third most important features across all the test data. So this pane here indicates a model that is biased but does not use the attack. And we see that the race feature is listed as the most important feature in every instance. However, when we introduce the attack, we also introduce two uncorrelated features with the race feature. So although the model is making predictions on the in-distribution data using the race feature, on this out-of-distribution data, the model uses this uncorrelated feature that has nothing to do with these predictions. And we see that when we introduce the attack and use these uncorrelated features, these are listed as the first and second most important feature in every case. So between this pane on the left and the two panes on the right, the predictions on the test data have not changed, yet the explanations have totally changed and do not indicate that bias is going on anymore. So we take this as the attack is quite successful. So moving on to how counterfactual explanations can be manipulated, we're going to consider a related but slightly different problem setting. So the adversary is interested in deploying a bias classifier, but here we interpret bias as a bias in recourse. So what this means is that between two groups in the data, so in a loan application setting, men and women, do people denied loans have similar recourse? So on average, we'd expect for a model to be fair, both men and women to have to do the same amount of work to get recourse. So the adversary wants to deploy a classifier where men have a much easier time getting recourse in this loan application setting. Yet regulators will audit the classifier's recourse fairness. So they will look between both groups and see, does recourse unfairness occur? So the adversary wants to deploy a model that is recourse biased, yet regulators do not see this bias. So how is this possible? So the solution that the adversary can employ is that an adversary builds a model that has equal cost recourse. So between both men and women, here we see an example from a loan application setting in our paper. Between both men and women, there is similar higher cost recourse. However, if we just the adversary can set up the model in such a way that under a slight perturbation, the model produces very low cost recourse. So if they just simply perturb male instances when they occur, the model will generate very low cost recourse. And while the model looks unbiased on the original data for this perturbed data distribution, the model will be unbiased. So the adversaries can accomplish their goal in this sense. They can generate low cost recourse and perpetuate bias simply by perturbing data points. So why is this possible? So we see that many types of counterfactual explanations hill climb the objective. So here is a loss service for a model. And if we just run a popular counterfactual explanation known as Water's algorithm, we see that for this original instance X, the counterfactual is all the way out here. However, we can design the model in such a way that under a slight perturbation, the counterfactual returned is much closer. So here, A of X plus delta, where delta is the perturbation. And we can actually design an objective to satisfy all the constraints that we've set up so far. So we can set up a model that is fair between both groups, but under a small perturbation delta, the model produces very low cost recourse, establishing unfairness. And we can incentivize the model such that this perturbation is small, and also that accuracy is maintained. And I'm not going to go into all the details. I encourage you to check out the paper for how we actually optimize a model that does this. But we can see, for an example on the communities and crime data set, between two groups in the data, the recourse costs between both groups look about the same. However, when we add the perturbation for members of the non-protected group, the recourse cost goes way down. So we see that the adversaries can successfully perpetuate bias in this setting by simply introducing this perturbation. We see that the recourse cost is much lower under delta.